Now, we have talked previously about subgroups, and in these couple sections we're going to introduce one particularly important subgroup of the permutation groups. Okay, so let's begin. Now, we know that we can write any permutation as a product of transpositions. But that representation is not unique. For instance, the identity can be written in several ways. You can verify that all of these are representations of the identity. Notice, in fact, I could write any sequence of 2 cycles and then write them in reverse order, and that would give me the identity. And you can think about why that is. See, here you have, you look at this one here. That's exactly what I've done here. These, if you take these and you reverse them, you get the identity. And that's always going to happen. So you can think about why that is. For some reason, however, this is 2 transpositions, this is 4, this is 8. We're always getting an even number of transpositions over here to get the identity. So this seems to be a strange fact. I always need an even number of transpositions to get back to the identity. Now, if you can find a product of an odd number that gets the identity, then you get an A for this course, and you probably win the Fields Medal. So this should probably be very, very hard to find an odd number of transpositions that gives you the identity. Okay, so in fact, it's impossible, which is what we'll be showing in this section. Okay, so in order to see why this is, let's investigate what happens when we multiply a cycle with a transposition. And that's what we're going to do in this series of exercises. Consider this cycle. Suppose I multiply this cycle on the left with the transposition AB. Okay. Now you can see how this is going to work. If I take this cycle and I multiply on the left by the transposition AB, or I shouldn't do it that way. AB looks like this. What's going to happen? Well, think about, for instance, what happens to the element here. According to what we've shown before, this element will go to here, but then when I take this over here, it goes to the element B. Okay. On the other hand, what does this element go to? Well, this element is going to go to B, and then when I go over here, the B is going to go to A. So you can see what I've done essentially is I've cut the permutation in 2, and then I've spliced up the 2 halves. Okay, so the action of this 2-cycle AB on this cycle is essentially to break this cycle up into 2 smaller cycles. This cycle has length 1, 2, 3, 4, 5, 6, 7, 8. This cycle has length 1, 2, 3, 4, 5. This cycle has length 3. Notice the sum of the lengths of these cycles is equal to the length of this cycle. Okay? And what you're going to do is investigate not just how this transposition affects this cycle, but you could also have a transposition that switches to consecutive ones, or there are several cases of transpositions multiplying by cycles. Okay, so you're going to investigate that, and you'll see what multiplication by a 2-cycle. So here are the different cases you can see. You could take a transposition of 2 points within a larger cycle. You could take a transposition of 2 consecutive points within a larger cycle. You could take a transposition of 2 points on 2 different cycles. You could take a transposition where one point is on a cycle and the other point is not on any cycle. You could take the transposition between 2 isolated points, or you could take, sorry, what I mean is you could take a transposition of 2 points that are in a 2-cycle, or you could take a transposition of 2 isolated points. So if we characterize all of these cases, we should be able to exhaustively tell what happens when we multiply a permutation by a 2-cycle. Because when you multiply a permutation by a 2-cycle, one of these possibilities must happen. And what you're going to do is you're going to catalog the effect of these multiplications by 2-cycle on the cycles involved. Okay, so this is a long exercise where you get to discover this. And it turns out that for a certain type of permutation called even permutation, the only way to represent even permutations is with an even number of transpositions. And for a certain type of permutation called odd permutation, the only way to represent them are with an odd number of transpositions. So this is something that you're going to investigate and learn by the discovery method. Okay, so all right, now let's consider even and odd permutations. So consider the symmetric group Sn. Now it turns out that permutations are either even or odd, because they can either be represented as a product of even number of transpositions or as a product of an odd number of transpositions. So we've broken Sn into 2 disjoint sets. In fact, this is a partition of the symmetric group. Okay. So that relates to this exercise here. All right, so the question arises, is it possible that An or Bn is a subgroup? Okay. Remember, An is the set of even permutations and Bn is the set of odd permutations. Well, actually, you can eliminate one of these right away because subgroup has to have the identity, and only one of them has the identity. Okay, so that's the content of this exercise. So we'll focus in on the even permutations, and we'll see that the identity is an even permutation, as we indicated from earlier. You'll show that any even permutation has an even inverse, and we'll also show closure. Okay. Turns out that the even permutations are indeed a subgroup of the set of permutations. And this is called the alternating group. So An is the alternating group on n letters. Okay. So we have the group Sn, and we really know how many elements there are in Sn. Just as a reminder, if I have n numbers, and I want to find out how many possible bijections there are from these n numbers to these n numbers, this is kind of a counting problem. Well, 1 can go to any of n possibilities. Once 1 is fixed, then 2 can go to n minus 1 possibilities. Once those 2 are fixed, 3 can go to n minus 2 possibilities, and so on down to 1. So I have that the order of Sn is n factorial. Turns out that the order of the alternating group is n factorial divided by 2. In fact, there are just as many even permutations as there are odd permutations. So they split the alternating group, they split the symmetric group exactly in half. And that's what's going on in this proof here. And you show that there's the same number of elements of An as in Bn. And it turns out you can show they have the same number by creating a bijection between An and Bn. Okay, and here's the bijection. I'll take any even permutation and compose it on the left with this 2 cycle, with this transposition 1, 2. Now, if you can show this is a bijection, then if you can show this is a bijection, then that means the domain has the same number of elements as the codomain. Now, when we consider it as a function, it turns, you want to show that, in fact, this is a bijection from an to bn, that the range of f is, in fact, bn and not Sn. Okay, and then you have to show that if you restrict f, so you consider f from an to bn, then we do indeed have a bijection. And this is what you're going to do in this exercise. Okay, so here's some more exercises about the alternating group. And that's it for this.